All right, so our warm-up problem. Find curl of 3xy, z squared y, xy, z. So the curl, it's an idea so nice. In this problem, we're going to do it twice. All right, so you had a few minutes to look at this. Do we have an answer? D? 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 Okay, it must be D. And that's what I think it is too, so good. Woohoo! All right. Let's go through this. We don't want to spend too much time. But remember, in general, we should make a note. Curl that's the del cross our vector valued function. So this is the one that involves a determinant. So make sure you're comfortable with the idea of the cross product. So I would say work from the inside out. So in other words, first figure out what's happening on the inside expression and replace that. So we'll do a little side note. We'll take the curl of 3xy, z squared y, xy, z. And all right, set up our 3 by 3 determinant, I, j, k. Give yourself plenty of space because the functions might be a little bit lengthy to write down. 3xy, z squared y, xy, z. And it's your diagonal. So I partial y of xy, z. That would be xz, I. J partial z of 3xy. There's no z, so that partial derivative is 0. K, partial x, z squared y. Well, there's no x, so again, another partial derivative of 0. Then you have to do the other diagonals. So here we have a diagonal. Involves k partial y, 3xy. So that would be 3x. But because it's sort of the other type of diagonal, we subtract. Here, the next one, we have I and partial z and z squared y. That's 2zy. That's going to be in the I direction. And we need to subtract. Then we have our last diagonal, xyz, partial xj. So partial x of xyz is yz. It's in the j direction. We need to subtract. So that gives xz minus 2zy, comma, minus yz, comma, minus 3x. Now, if you weren't paying attention, what might you be tempted to do? You're like, hey, that looks like C. Yeah, we kind of know intermediate work will show up and we say, hey, let's throw it in there as a distractor. Don't be distracted, because what have we done? Well, we've gone one step. So now we say, okay, now our problem becomes find the curl of this thing we just found. So xz minus 2zy minus yz minus 3x. Now the good news is, because it's multiple choice, you actually don't have to do the whole thing. You just have to do just enough to say, which one is it? And in other words, you can say, look, if I can eliminate an answer, or if I can eliminate all the answers, then I'm good to go. So notice that, for instance, they all have different entries in the first slot. So that just means if you compute just the first slot, that's enough. Now we'll compute the whole thing, but I just want to note, you can save yourself some work if you want to. So diagonals, derivative with respect to y of minus 3x, well, 0. So you get 0i. Derivative with respect to z of xz minus 2y, well, that's x minus 2y. And finally, derivative with respect to x of minus yz, well, that's again a 0. Start going the other direction. Derivative with respect to y of xz minus 2zy, well, that's minus 2z. But we're going to subtract that. And at this point, we actually can tell the last slot is going to be positive 2z, which is d. So we know d is the right answer by this stage. Next diagonal, we're going to take partial z of minus yz. So that's going to be minus y. but we're going to subtract it. Then the last one, we're going to get partial x of minus 3x, and that's a minus 3, but we subtract that and put it all together. 0 minus minus y plus y. Here you get a minus minus 3, which is a 3, plus x minus 2y. And 0 minus minus 2z is a positive 2z. So there you go. All right, any questions on this one? Okay, cool. Well, moving to today, well, let's start. A thought for the day. Conan O'Brien, of course, Conan O'Brien, well known for his work as being a staff writer for The Simpsons. Actually, he's probably better known for other things, but he's had an interesting career. And so he says the following: if you work really hard and you're kind, amazing things will happen. I think this is a great advice. I like this. Now, of course, notice he doesn't say you'll get rich, but amazing things will happen, and I do like that. I do think that success in whatever you're trying to do oftentimes comes as a combination of hard work and working with others. And if you want to work well with others, learn to be kind. I will say I have seen bad advice. I tend not to share that. But there was a well-known person who worked in sort of the border of engineering, electrical engineering, and mathematics. And he gave a talk, and after the talk, they're doing some question answers. And he said, well, you can either be a great scientist or a nice person, but you can't be both. And that's not true. You can be a great scientist and you can be a nice person. Yes, there are examples that show there are some great scientists who aren't nice. But I have met many people who are both very smart, very successful, and are nice people to be around. They're people you want to be around. And so I encourage you, be kind, work well with others, and work hard. Now, what's our goal for today? We're going to get back into integration. We're going to talk about line integrals, and we're going to talk about two settings. So we'll start with integrating along a curve, f of x, y, ds, and this seems sort of not right, because this seems like, wait a second, this looks like a one-dimensional thing, but now I see x and y, that feels like a two-dimensional thing. We'll explain what all of that means. But then there's a second setting which says integrate along a curve of your f dot t ds, or sometimes it should integrate along your curve m dx plus n dy, where m and n are functions. Now in both settings, the way we're going to do it is we're going to say put everything in terms of some parameterization t. So that's the idea. And so at the end of the day, it's like, oh, it's just rewriting it to something we're familiar with. But there's an important distinction between these two. And I just want to, before we dive into it, I want to point this out. In the first version here, orientation doesn't matter. In other words, I don't care which way I move along the curve. I just care what the curve is. So I don't care, do I travel left to right or right to left? Doesn't matter. In the second version of line integrals, orientation matters. And that is to say, if I travel in the opposite direction, I flip my sign. Now, channeling your vast experience with calculus, because you've been studying calculus now for, this is your third semester. Some of you may have started even before then. Between these two, which one do you think is going to be the one we're going to focus on after today? Do we care about orientation, or do we not care about orientation when we're in calculus? What do you think? Does orientation matter? I guess is the question. Do we really care that much? Or is it just sort of like a fluke? And I know at this point you're like, I don't know how to answer your question, Steve. So are you like, orientation yes or orientation no? What do we think? We are orientation yes people. We like orientation. And a big piece of what's happening in the next couple of lectures, right up to the end of the semester, is we're going to start building up on this idea of we need to make sure we understand our orientation. So orientation is going to play a role in what we're doing. Now, in terms of our formula sheet, there's not much going on today, but I will point out that this ds, we've seen essentially before. It looks a lot like what we saw for arc length, because it's arc length. And so ds is the square root of x prime squared plus y prime squared dt. That's for 2 dimensions. 3 dimensions, you get a similar expression. All right. So let's begin. So we'll start with the basic idea of line integrals. Now, we understand integrals from Calc 1. We have this sort of notion, if I'm integrating a function from a to b, so here, this curve, this is my curve f of x. Then I say, oh, well, the integral from a to b of f of x dx, it's like the total. And oftentimes we start by saying, oh, it's like the area, but we put area in quotes because it could be positive, could be negative. Now what we're going to say is, well, let's try to put this into a new setting, where instead of having a straight line segment that we go over, maybe we're going over some curve. But we still can say for every point on the curve, there's a height. And the height now depends where you're at. So given a point xy on the curve, the f of xy is your height. So you have a height, that's your f of xy, and ds, you just imagine you're breaking your curve up into little pieces. And so ds, that's your width. So it's height times width added up over the curve. And that finds the total. So you might say, well, maybe you're making some drapes for a theater where the curtain has sort of an interesting circular bend to it or something for where the drapes hang. How do you find the total amount of material? Well, it's just, okay, find the height, find the track it goes over, and you add it up. So no big surprises. And you should start to pick up on a few things. One big thing you should pick up on is the number of integral signs. So that's telling you the dimension of what you're looking at. So if you see a 1 integral sign, it says, oh, it's like a 1-dimensional integral. 2 integral signs means it's a 2-dimensional integral. 3 integral signs means it's a 3-dimensional integral. 4 integral signs means you're in the wrong class. So we'll stop. Of course, you can do any number of integral signs, but we'll only see 1, 2, or 3. So 1 integral sign means it's an inherently 1-dimensional thing. So even though it looks like there's more than one variable involved, it's actually not. It's just a way to incorporate the height. So I say, okay, great. We're trying to find the total area of what's under this surface, right? This is just a piece of a surface straight down to the curve. If we drop straight down, what's the area? Well, of course, you do what you always do. Break things into small parts, find the contribution of each part, add up to find the total. Classic Calc 2 kind of ideas. So we say, well, we just have to find our pieces. So our width. Well, S, we've talked about S way back. It was just before the first exam. So S stood for cumulative arc length, or if you like, cumulative distance. So that was what S was. Now, how do we find it? Well, if you think of S as distance, take the derivative of distance with respect to time. Derivative of distance with respect to time, what are you measuring? Well, it's not quite velocity. What is it? It's speed. So what you have, the derivative of distance with respect to time is speed. You say, well, we know how to find speed. It's the magnitude of velocity, which is the square root of x prime squared plus y prime squared. So this becomes, if I want to know what's a little bit of distance, a little piece of distance, it is, in terms of t, the square root of x prime squared plus y prime squared times your piece of t, dt. So you say, all right. So that helps us understand how we're going to rewrite this last piece, the width in terms of t. We say, but the function, f of xy, the height, that's pretty much a freebie. So what we can do is we say, pick a parameterization for your curve. Now, which parameterization should you pick? It turns out that if you have a single curve, there can be multiple different parameterizations that work. Which one should you choose? The answer is, be nice to yourself. Pick the simplest parameterization that captures that curve. If you pick a different one, you'll still get the same answer, but the computation may be a lot more unpleasant. So pick a nice, simple parameterization, and then say, all right, so if we're adding up the total, it's the sum of our height, width. Our height is just what's the height at a particular time. So you plug in x at that time, y at that time to figure out your location. Plug that into f. That gives you your height. We've already talked about how to figure out the width in terms of t. And so that gives us our integral. So the whole idea is we're going to take this and we're going to rewrite this as a normal integral with respect to time. Okay, so that's the basic setup. Any questions? Okay, so let's try an example then. Find the integral along the curve x squared y ds, where c is the portion of x squared plus y squared equals 9 in the first quadrant, going from the point 3, 0 to the point 0, 3. Now, x squared plus y squared equals 9, what is that? It's a circle of radius 3. Okay, so there's our circle radius 3. Here is the point 3, 0. Here is the point 0, 3. And we're going from 3, 0 to 0, 3. So currently it says go that direction. So we need a parameterization that will work for us. Does anybody have a candidate parameterization? If not, I'll give you a candidate one, and then you can say, no, I don't want that one, and then we can work to find a better one. All right, so does anybody have a candidate parameterization? So here's one, x of t, y of t, that we could choose. Namely, do 3 minus t and comma, the square root of 9 minus 3 minus t squared. And that's for 0 less than or equal to t less than or equal to 3. We can do that. That starts at 3, 0. It ends at 0, 3, and it follows that curve. However, this has something unpleasant. So it's probably not the simplest option. So let's see if we can't do better. Do you have a different idea of how to parameterize this curve? Sorry, what? Well, polar would be if we were trying to describe a region. But I do like the sort of the philosophy of polar. What does polar use? Well, it uses like angles, right? So let's see. I'm trying to think of a good way to say this without giving it away. Does anybody know a good parameterization for a unit circle? What? I see one finger there. A parameterization for a unit circle? Well, that's R equals 1. That's a description, but I'm thinking about like something that moves along a unit circle. Cosine for what? X. And sine for, well, I'm asking so we can figure it out. Oh, no, okay. Sine for the y variable. So you probably learned about in trigonometry that there's this idea of trigonometry on the circle. You say, oh, every single point in the circle, you have like a cosine angle and a sine of an angle. So it turns out that you can actually use that to get a parameterization. So we'll do a little side note here. For the unit circle, so here's our unit circle. The cleanest way to parameterize it is cosine t, sine t, and then you just let t be whatever you need to grab the part of the circle you want. Now you might say, that's great, but that's a unit circle. This is not a unit circle. Well, we have ways of making it work. What's the difference between the unit circle and the circle we're looking at? It's 3 times bigger. So what do? We multiply by 3. So if you need to be a bigger circle, add whatever your scaling factor is in front of your cosine and your sine. So you get 3 cosine t, 3 sine t. Now, where does t go from? Right, so 0 less than or equal to t less than or equal to pi over 2. Both will give us the same answer, but this will likely be a much simpler integral. So let's carry out the computation. So if we're doing the integral along c x squared y ds, well, our bounds will be based on our t bounds. So our bounds are going to be from 0 to pi over 2. Our x, so this is our a, b, our x is 3 cosine t, our y is 3 sine t. And so we're going to have 3 cosine t, quantity squared, 3 sine t. So this is our x squared y. What else do we need? The ds. We have to rewrite that. So this is when the sine and cosine really shines. So ds is the square root of our x prime squared plus y prime squared dt. What's the derivative of 3 cosine t? Negative 3 sine t. It's negative 3 sine t squared. What's the derivative of 3 sine t? 3 cosine t squared. And if we carry out this computation, well, you'll get 9 sine squared plus 9 cosine squared inside the square root, which becomes 9 in the square root, or 3 once you do take the square root. So it becomes 3 dt. So ds on a circle, if you use a good parameterization, it's very clean. So that 3 dt, this is your ds. So we rewrote everything in terms of our t. Well, we've got a bunch of 3's, so we'll count them up. There's 3 squared, one more 3, and one more 3. So that makes 3 to the 4th. I'll put that in front as 81. So 81 integral 0 to pi over 2 cosine squared t sine t dt. All right, so that's the integral we have to do. What will that give us? How do we find this integral? U sub. What should we U sub? U equals cosine t. If you say U equals cosine t, du is negative sine t dt. Now, very convenient for us. So what do we get? Well, we're going to get a negative 81. The negative, because of this negative, integral u squared du. And what will our bounds be? Cosine of 0? Cosine pi over 2? 0. Now, because of orientation, we can flip the bounds and we change the sign. So this is 81 integral 0 to 1 u squared du. What is the integral of u squared du? Yeah, 1/3 u cubed. So 1/3 times 81 makes it 27. Evaluate from 0 to 1. We end up with 27. Wow. Cool, cool. It works like a miracle. All right. Any questions? Where did this come from, or where did it go to? Well, notice how we had our bounds were 1 to 0? We flipped the bounds, 0 to 1. So that's where the negative disappeared to. Now, how are we doing? We're doing all right. We have all the time we want, right? I made a claim earlier that the orientation doesn't matter. I want to try to verify that. So we went from 3, 0 to 0, 3. What if I wanted to go from 0, 3 to 3, 0? Well, I claim we can do that. Here's what can you do to your parameterization to make that happen? So here's sort of a fun idea. Imagine you have like a spatula. You pick it up, turn it over, put it back down. Then, if you were going from 3, 0 to 0, 3, now you'd be going in the opposite direction. So what's the effect of picking it up, turning it over, and putting it back down? So you're flipping across the line y equals x. How do you achieve that effect?
You flip your x and y, so x would be 3 sine y.
Yes! So this goes in the wrong way. So we're going to do it the wrong way. Wrong orientation. And I just want to point out what happens. So we go through, the ds is going to be the same thing. So it's going to become the integral along your curve, x squared y ds. Well, it's still integral 0 to pi over 2. Now it becomes 3 sine t, quantity squared, 3 cosine t, and it's still 3 dt. But what happens? Well, now you make a different substitution because it's sine squared cosine t. So what's your substitution here? You choose u equals sine and du equals cosine t dt. So what you end up with is you end up with 81. You still have the 3 squared times 3 times 3. Your bounds are going to be from sine of 0, which is 0, to sine of pi halves, which is 1, u squared du. Well, that's exactly what we had at this stage. So we still got 27. So if we went one direction or the other, in this format, orientation doesn't matter. You're still going to get the same answer, which seems wrong. But we'll switch to a different one in just a second. All right. Well, let's do quickly the 3D version. So the 3D version, again, you can have a wire in space, for instance, is oftentimes how we think about this. But you have an integral along a curve in three-dimensional space, f of x, y, z. Now, instead of thinking about it as height, you can think about it as density. Right? That's a very convenient way to think about what's going on. What do? You do the exact same process. Write everything in terms of t. So you have a to b. That's your bounds. And so I should put a little note here where c is what? You have your parameterization, x of t, y of t, z of t, where t goes from a to b. So you put your bounds from a to b, replace the x, y, z by the parameterization for x, y, z, and then this long piece on the end is your ds. So here's a question. Find the center of mass of a thin wire modeled by this curve. So this is our curve, c equals cosine t, sine t, comma t. Does anybody recognize what this curve looks like? It is the helix. Yes. So it starts, if we have our x, y, z, it will start down here, and it will spin once around. So it's just doing a one trip around the z-axis, and as we move around, the height goes up. But our density also increases. So at the bottom, very small density, but by the time you get to the top, much higher density. So the density shrinks the lower down you get. So more density, the higher up you go. So the top of it weighs more than the bottom, or has more mass than the bottom. All right, so if we want the center of mass, what do we need to do? How many integrals are we going to need to carry out? 4 integrals! Yes, unless we have symmetry. Do we have symmetry? No! We don't really have the symmetry we need. So that means 4 integrals. So we're going to get like super good at these integrals. Or maybe they'll all be super straightforward. Okay, so let's think about what do we need. If we're going to turn our, this has now become a bit of a project. The first thing we need to focus on, I think, is just making sure, what is this? We already have our parameterization, so we're going to find our ds. All right, so that's the square root of x prime squared, so minus sine t squared, y prime squared, cosine t squared, and then derivative of t is 1 squared. So you get sine squared plus cosine squared plus 1. What's another name for that? It becomes 2. So square root of 2. All right. Well, that actually was faster than... Good. Nice. So let's start with mass. How do you find mass? You integrate what? You integrate density. So for us, it's the integral along the curve. Our density is z. So that's the integral we have to do. When we rewrite this in terms of t, well, it's going to become integral from 0 to 2 pi. Z becomes t, and ds becomes square root of 2 times dt. That becomes square root of 2 over 2 t squared. Evaluate from 0 to 2 pi. Plug in 0, you get 0. When you square 2 pi, you'll get 4 pi squared. But we also have it divided by 2, so we end up with 2 square root of 2 pi squared. So that's our mass. What else do we need to compute? Give you a moment to think about it, but not too long. At best, we can only afford 3 moments. So our moment, integral c, distance, density, ds. So there's going to be 3 moments. So which one do you want to focus on first? Well, and in 3 dimensions, we talk about moments with respect to the planes, xy, xz, yz. We can go in any order. xy. What's the distance to the xy plane? Z. So you get z, distance, z, density, ds. So you say, great. This becomes integral 0 to 2 pi. Z becomes t. So we get t squared. Right? T, ds, root 2, dt. Well, okay. That's root 2 over 3 t cubed. Evaluate from 0 to 2 pi. And we end up with a number 8/3 square root of 2 pi cubed. Yes? What's our next moment we're going to tackle? YZ. All right. Cool. Moment with respect to YZ. What's our distance to the YZ plane? It's x. Z is our density, ds. So we get 0 to 2 pi. X is cosine t. Z is t. And then ds is square root of 2 dt. Well, do we know how to integrate cosine of t times t? Well, there was a note they gave us. The integral of cosine of t times t is t sine t plus cosine t. So this becomes square root of 2 times t sine t plus cosine t. Evaluate from 0 to 2 pi. When you plug in 2 pi, sine of 2 pi, 0. Cosine 2 pi, 1. When you plug in 0, 0 times sine of 0, 0. Cosine 0, 1. Giving us 0. Was that obvious beforehand? No. I don't think it was obvious. But let's find out. What are your predictions? We have one more, xz. The last one was 0. So what do you think? Will this one be 0 as well? One way to find out. What's our distance to the xz plane? Well, we have to know the distance for the form. Oh, you meant the variable y. Oh my gosh, I can't believe I did that twice in one day. All right. All right, but what is y? Y is sine of t. So we get 0 to 2 pi, sine t root 2 dt. And they told us how to integrate t sine t. So we have a root 2 out in front, minus t cosine t, plus sine of t. Evaluate from 0 to 2 pi. When we plug in 2 pi, what do we get? We're going to get negative 2 pi. And then sine of 2 pi is 0. When we plug in 0, what are we going to get? We'll get 0 because of the 0. And sine of 0 is 0. So we get negative 2 root 2 pi. Is it okay that this is negative? Yes, it's okay that moments are negative. Because moments are helping to sort of measure location in some sense. And it just says, I'm more biased towards the negative side. Mass, it's not okay to get negative mass. If you get a negative mass, something happened. And it wasn't a good something, to be clear. All right. Now, are we done?
No.
No. What's left? We got to take the ratios. So our center of mass, you take the moment with respect to y, z, divide by mass. Moment with respect to xz, divide by mass. Moment with respect to xy, divide by mass. That's on the formula sheet, so that's not too surprising. So we get 0 over 2 root 2 pi squared. Oh, that's going to be easy to do that computation. Minus 2 root 2 pi over 2 root 2 pi squared. Right, that's the next computation. And I'm running out of space. You're probably thinking, Steve, you ran out of space a long time ago. I understand how you feel. 8/3 root 2 pi cubed over 2 root 2 pi. All right. Let's see. We'll put it up here. 0 over 2 root 2 pi squared. Another way to say that? Yes. Here we have a 2 root 2 pi. The 2 root 2's cancel. One of the pi's cancel. We're left with a minus sign upstairs and a pi downstairs. Minus 1 over pi. And here we have a root 2. That cancels. We get one of our pi's to cancel. So there's a pi squared left upstairs. And let's see, what else do we have? Oh, wait, I get 2 of the pi's. There's a pi squared here. So there's just 1 pi left upstairs. Okay, so there's 1 pi left upstairs. I can also divide the 2 into the 8. That's 4. So that leaves us with 4/3 pi. And there we go. There we go. We almost fit it on a page. It's pretty close, but it's kind of there. All right, good. Now we still have one more idea left. Okay. Last sort of idea for the day. We want to talk about work. And so we'll do just a little bit of physics. So how do you compute work? Now, when you first take physics, we just say, oh, work is force times distance. And you're like, that's cool. Nice. And then you learn about vectors, and you're like, oh, it's going to make things more complicated. And then you learn about the dot product, and it's like, oh, no, it's just instead of force times distance, it's force dot displacement. And so the analogy I like to give is if you have a bunch of people who are pushing a car that has died for some reason, you say, well, how much work is going on? The people who are pushing directly behind are much more effective at doing work. The people that are pushing at a slight angle are not as effective because some of their force is getting wasted pushing into the side, and then only some of their force is moving it forward. You know, and then of course, and I hate to pick on art history majors, but if you had an art history major pushing here, no work is being done, right? So you have to keep in mind, how are these vectors related? So that's why there's this dot product. It's how much of the force is actually helping you move it forward. So our idea, we're trying to move something from the start to the end. And we say, all right, how do we find that? Well, what we'll do is we'll just chop things up into little tiny pieces and say, instead of trying to figure out the entire work all at once, do a little tiny piece. Nudge it a little bit. So there's the force. Then you have to say, what's the displacement? So that gets back to, what was T? Do you remember T? This capital T? It was our tangent vector, our unit tangent vector. So it was the direction of the curve at that point of length 1. So here you have direction. I should choose a non-red color. So this is a direction. That's captured in T. And delta S is a length. So now, length times direction, that's the vector. So you just move it a little bit. So that's our vector, that is our displacement. Well, add it all up, take the limit. You say the work is the integral along the curve of f dot t ds. Most of this is just a reminder. What is t? Well, it's the unit tangent vector. The derivative of your curve, that is your direction of motion. To make it a unit tangent, you normalize it or scale by the magnitude. And at this point, you're like, no, not another square root. How many square roots do we have to endure? But the magic is you have 2 square roots, one from t and one from ds. And they cancel. Oh, happy days, happy days. So then the rest of this is just to say there's some cleanup of notation. We can write this as dr or individually dx, dy. But the punchline here is you don't have to do square roots when you're doing these oriented integrals. And in particular, it says, look, no square roots matter. Sorry, no square roots needed. Orientation matters. You have your f dot t ds, which is integral of f dot dr, which is integral of m dx plus n dy. Now, really quickly, because I know I still have like a few seconds left, why does orientation matter? Well, notice, if you're going from start to end, that gives you a direction. If you go from end to start, you'd point the other way. You'd flip the sign of t. Flipping the sign of t is what gives you your orientation. All right, we'll start here next time with some examples of how to carry out these integrals. Have a great day.